My name's Dr. David James. I'm a lecturer in sports engineering at Sheffield Hallam University. Our lecture for the Institute of Physics Schools Lecture Tour is really a story about the interaction between physics and sport. We delve into 3 different Olympic sports and we unpick the physics that governs those sports. And really it's all about forces in motion, it's all about Newtonian physics, and we deal with this sometimes quite a challenging topic through the context of sport. And I think the students find it really, really exciting and interesting. I think I probably first got really interested in physics at some point in secondary school. I think I remember being taught about, particles and then atoms, and just being amazed that there was this world that we can't see with our own eyes, but that is absolutely fundamental to everything we do. And this idea that there's this incredible unseen world that explains everything, for me that was just such a fascinating idea, that there was this incredible unseen world out there. I found that it's really turned me on, and I just really had to know more. Welcome to the marvellous Royal Institution. My name's Dr. David James, and I'm here today with 2 of my colleagues from the Centre for Sports Engineering Research at Sheffield Hallam University. So we've also got Leon Foster and Sean Clarkson, who'll be helping us out over the next hour. Obviously, we've got the London 2012 Olympics just a few weeks away now. It's been a huge build-up. I'm sure it's going to be a fantastic games. But throughout that event, I'm sure you'll probably start to see this as I go through this. Well, I hope that when you see that event, you'll see that there's so much science going on sort of behind the scenes all the time. So, first of all, I'll tell you a bit about who we are and what we do. So I call myself a sports engineer, and we've got a research centre up in Sheffield. And we do lots of different things. Essentially, we try to kind of understand the fundamental physics of what happens in our sports, and then we use that knowledge to try to create new products, create ideas, to work with athletes, to make them be better at what they're trying to do. So sort of things we do. We look at things like forces are very important to us, understanding what the fundamental forces are, where they're acting, how big they are. That's a really good starting point. We also spend a lot of time looking at materials. The world of sport's gone through a sort of a revolution in terms of the materials that get used. So, for instance, tennis rackets have developed from, say, wooden tennis rackets in the sort of late 1970s and early 1980s into carbon fibre tennis rackets today. That's actually quite a recent change, but a very, very dramatic change. So you might see John McEnroe on the television over the next couple of weeks as he commentates on Wimbledon. Well, of course, he used to play tennis with a wooden tennis racket. And so these things are changing. And not just that, obviously, we've got the European Football Championships happening at the moment as well. Well, football in the 1960s was played with leather footballs that used to absorb moisture off the grass and rain, and used to double in mass during the game. And of course today we play with balls that are quite different, thermally bonded synthetic balls that are altogether quite different really, and that has implications for how the game is played. So materials are really important to us. I guess another area of things we look at is we look at friction and traction. So obviously in this case here we've got an athlete who's clearly lost some traction and has probably lost the point as a result of that. So understanding how friction and traction works is really key. But it's not always just about, say, footwear. It could be about how, say, a swimmer is moving through the water, or how a cyclist is moving through the air. The role of friction in sport is really critical. So we try to understand it, and sometimes we're interested in trying to minimise it, say for the cyclist or the swimmer, but in other cases we're trying to maximise the friction. But we can't go too much, because for instance in this case if you had too much traction on your feet you might end up actually doing yourself an injury. So it's actually about optimising the amount of friction that we've got. So it's quite a difficult problem often. And I guess the final thing that we focus a lot of our efforts on is it's trying to measure the world of sport. Sport's very complicated, lots of things are happening, people are running around all over the place, balls are flying from left to right, and all sorts of different things can be happening. And actually, information is one of the key things that can really drive performance. If you can measure what an athlete is doing, you can provide really valuable information, say, to the coach, so that athlete can train better, train harder, train more effectively. So increasingly, what we do is we're actually about measuring everything that's happening in the world of sport, and then trying to decipher all that data, analyse all that data to pull out the really important things that actually mean something. So we're working at the moment with 14 different Olympic teams, all Team GB, glad to hear, and I think about 20-odd different projects with those teams as well. And it's all about trying to measure what our athletes are doing and then filtering that information back to the coaches so they've got a better idea of what they should do. And of course, it's not just about providing information, say, for the coaches. Sometimes it could be about providing information for the referees. So, goal line technology being a key example of how we might want to measure something, so that can actually sort of have an influence maybe on the outcome even of some games. There are sort of key areas. What I'm going to do in this talk, I'm going to talk you through a number of different Olympic sports, and we're going to have a look at the underlying physics behind each of those sports. So our first sport to look at is the long jump. I guess we're going to start off with a bit of a scientific hypothesis, and that is that top sprinters equal great long jumpers. As a question, do these two disciplines go together very nicely? There's quite a lot of anecdotal evidence to suggest that this might be the case. For instance, Jesse Owens in 1936 is one of the all-time great athletes. He won the 100-metre sprint and he won the long jump. However, that's just one example, so I don't know, maybe it's true, maybe it's not. We've got some other examples as well. We've got other fantastic athletes. Carl Lewis, again, an amazing sprinter, won gold medals in the 100 metres and also won gold medals at the long jump. So you've got the athletes seem to be able to move between these disciplines quite easily. And also, of course, Marion Jones, slightly more recently, winner of the 100-metre sprint and at the long jump as well. But we can't just use, these anecdotal bits of evidence. We have to sort of really delve deeper into the data before we can start to maybe draw any conclusions. So what we've got here is we've got a massive data set, and I'll try and talk you through it. Essentially, what we've got here, so first of all, we've got, these are years, these are dates on the bottom, so we're going from 1918 up to 2010, 2014. And each data point represents the average of the top 25 performances in that year. So it's a huge data set, this. So we've gone through all the record books and figured out who are the top 25 competitors in any year. This is a global data set, who are the top 25, and we've figured out their average, we've plotted it on a graph. And we've got two data sets here, so it's a tiny bit complicated. We've got the 100-metre sprint in time here. So in 1922, if we go up here, we can see that the average 100-metre time for female sprinters was just more than 13 seconds. We've got another data set as well. We've got the long jump. Okay, so on the long jump in the same year, 1922, the average distance jumped was just about sort of 4.9 metres or something like that. So that's the data set we've got, and you can see there's been big changes. Okay, so obviously in the 100-metre sprint, times have come down really rapidly. They've kind of levelled off. Equally, in the long jump, distances have gone up and then levelled off. What I find amazing is they seem to be quite symmetrical in terms of the shape and the profile. They've got very similar features. So for instance, here and here, you see there's sort of this dip in performance. And that coincides with the Second World War. So I think it's really fascinating. So during the Second World War, obviously, it's has such a global impact on our world that people just couldn't participate in sport. They had far too many other things to be worried about. So sporting performance dropped. We see another interesting trend here is that really both in the 100 metres and especially in the long jump, after sort of 1989, 1990, performances level off. Or they go down until that date, and then it goes level. What's quite interesting here is 1989 was the year that widespread drugs testing was introduced, and that's when we see a very significant change in how our athletes are performing. Now, I'm going to just manipulate this data slightly, and what we've done here is we've actually represented the 100 metres, not in time, not the performances in time, but in actual speed. So average speed, and that means that we can just compare these two data sets a bit easier. So you see they're very similar. We can actually correlate these two data sets now, plot them against each other, and we get this really nice correlation. Very, very strong correlation indeed. So they all line up on a line, and so we've got the female data there in the red dots, and then the blue dots are the males, and it's all on a nice sort of flat, straight line sort of continuum there. So we've got a very, very strong relationship. That's a highly significant relationship. That means I think something really interesting is going on here. So we're pretty sure that there's a very strong link between running fast and being a good long jumper. It's pretty confident about that. So I guess the question we kind of now want to ask ourselves is, well, this guy, Usain Bolt, he's the fastest sprinter in the world. So how far could he jump? He doesn't do the long jump, but just theoretically, ask ourselves the question, how far could he jump? And to do that, we're going to have to delve into the physics of this event. So what are the physics of this event? Well, essentially, the long jump is really a case of sprinting down a track, got 40 meters, run up, you hit the board, and then you've got to jump as far as you possibly can. Once you're in the air, your movement through the air acts like a projectile. You might have heard of projectile motion in your school lessons. Well, as a long jumper, once you take off, your movement through the air is that of a projectile. And we've got some good physics that can explain projectile motion. So this will help us to understand this question, or push forward on this question as to how far could Usain Bolt jump. So what is projectile motion? Well, essentially, projectile motion, we've got some equations that can explain really the path of an object as it flies through the air. Given us an initial set of conditions, say its launch angle and its launch speed, where would it go? What would the range be? And it all depends, because it really depends on the angle that you take off at. So if you take off at a very steep angle, you're not going to get particularly far, because you're essentially using a lot of your speed just to go high, then you're going to come down. If you take off too shallow, again, you're not going to have enough height to get the range. And of course, what we find, and I'm sure many of you will kind of know this, if not theoretically, but maybe through experience or just intuitively, you'll know that the optimum angle to get the maximum possible range is 45 degrees. So literally halfway between being horizontal and vertical. That's the optimum. We've got some sort of nice bit of physics, nice bit of maths to explain that. Essentially, the distance that we're traveling, that's the thing we're interested in. So d is the distance. Okay, v squared, so it's velocity times itself. That's the launch velocity. That's how fast we're sort of launching at. G here, that's the gravity. That's the acceleration due to gravity. So when you kind of know this, if you hold something in there and you drop it, it accelerates downwards due to the Earth's gravity. And it accelerates at 9.81 meters per second. So that's the acceleration due to gravity. We've also got the launch angle. So there are our key things. And really, the two things that we can change as a long jumper are our launch velocity and our launch angle. If we take off at 45 degrees, we get the maximum range. And of course, the range we get is also dependent on how fast we run, really dependent on how fast we run, because it's a squared relationship, so you times it by itself, so that becomes really, really dominant. Now, things are a bit more complicated in the long jump, and they often are. We start off with these sort of nice, simple ideas and quickly find out they're a bit more complicated. And one of the complicating factors in the long jump, when you're doing the long jump, there's actually a difference between your takeoff height and your landing height. And that's because you take off and you've got what we call your center of mass, somewhere in the middle of your body. And you take off, and that might be maybe a meter high or something like that on your takeoff. When you land, because you sort of bend over when you land, your landing height is different to your takeoff height in terms of where your center of mass of your body is. Now, this changes that optimum angle, and so it actually reduces the optimum angle down from 45 degrees. Because there's another problem as well, and that's that if you're a long jumper, you're running down the track as fast as you can, you put your foot down, it's pretty much physically impossible for you to take off at 45 degrees. you've got such amount of horizontal speed, it would take a monumental effort to jump upwards to get a 45-degree angle. It's just not possible. We haven't got the power in our legs to be able to do that. So what tends to happen is that athletes tend to take off with a launch angle of about 33 degrees. And if you measure loads of athletes, that's sort of seems to be the optimum angle that they take off at. And there's another thing that happens as well, and it's that when you do this takeoff, you put your foot down and you sort of jump upwards, you actually lose speed doing that. So you might be running along at your maximum speed, you hit the board, but then you lose speed in that takeoff moment, maybe sort of 10 to 20% of your running speed. So all that you have to sort of consider how all these things now play into it. I think we can deal with this though, and we can actually start to still answer this question. How far would Usain Bolt jump? We need to know how fast he can run first. That's one of the first things we need to know. And we've got some good data here. This is when Usain Bolt got his world record in 2009 at the World Athletics Championships in Berlin. Some scientists tracked his movement down the 100 meters. And effectively, we've now got this nice bit of data where we knew where he was at different stages in that race, and we've got a nice plot. Now, of course, what happens in the 100 meters, you don't run at a constant speed all the way along, because you start off stationary, then you accelerate to a high speed, and then maybe you sort of coast in at that speed. So your speed's changing throughout the race. And of course, I guess a lot of us would probably know as well that to figure out the speed that someone's moving at, we're actually talking about the gradient of this distance versus time graph. And the athlete's going at their fastest when that graph is at its steepest. And actually, if you see the graph is at its steepest around here, around the 40-meter mark, about 4.5 seconds. So what we can do is we can calculate the gradient of that graph, and that's the speed, the maximum speed that Usain Bolt can run at. So essentially what we do is we divide the distance travelled by time. So speed is distance divided by time. We kind of know that because we talk about miles per hour, distance divided by time, don't we? Figure it out, and his maximum running speed, in this event anyway, when he got his world record, was 12.1 meters per second. Just imagine, it's what it says, he's covering 12.1 meters in 1 second. And if you imagine this whole room, I'd imagine from that far end to that far end is probably about 10 meters. He's covering that distance in our seconds, to give you an idea of the amazing speed that he's travelling at. So we know the speed. We're pretty sure that's his maximum running speed. So how far could he jump? Well, we've got his max sprinting speed. Handily, he actually can reach that speed because he accelerates from 0 up to that speed, and he can do that in 40 meters, which is quite handy because that's the length of the run-up for the long jump. So he could hit the board at 12.1 meters per second. If we assume, say, he loses 15% of his speed, some athletes would lose less than this, but this is a sort of a conservative estimate. Say he loses 15% of that speed at takeoff. So he takes off at 10.3 meters per second. Assume he takes off at 33 degrees. So this is the sort of very well-known sort of takeoff angle. We can assume he's got perfect technique because he's a supreme athlete. He's mastered, running around corners. He's a very highly skilled athlete. So presumably he can master the long jump. He can have perfect technique. We can start to figure it out. So we've got our equation. If you remember this is our basic equation. Distance equals velocity squared divided by gravity times the sine of two times the takeoff angle, theta. So we can put these numbers into our equations. And we've got, first of all, the takeoff speed goes in. We've got gravity there, 9.8. Put the 33 in here. And we can figure it out. And quite amazingly, we reckon he can jump 9.9 meters. Now, that's quite surprising because it's a whole meter further than the current world record, which was set by Mike Powell almost 20 years ago. 9.9 meters is pretty amazing. Really. It's absolutely enormous distance. But we reckon, it's pretty likely he can do this. Now, that is a very large jump from a whole meter on the long jump. I mean, normally records do go up very sort of incrementally, maybe by centimeters. So, this would be quite a dramatic thing if it did happen. But after maybe Usain Bolt's mastered his sort of sprinting, you might want to move on to a different discipline, like the long jump, just like Carl Lewis did in the 1990s. He kind of did everything he felt he could do in sprint events, so he moved into the field events, which I think could be quite interesting. Okay, so definitely possibility for breaking or smashing a world record there. Just to go back to this graph that we started off with, imagine just where would Usain Bolt fit on this graph here? This is all the data, all these sort of sprinters and the distance that they've run. So where would he fit on this line? Well, incredibly, just to give you an idea, he's going to fit right up there, sort of way off, right up the top, but on the same line. You'll still be on the same gradient, just much further along it. So hopefully we'll see that in a few years' time, or maybe not. Maybe he'll decide he doesn't want to do it after all. Yeah, so some fascinating physics there behind just a everyday event. So when you see the long jump in a couple of weeks, just have a think about that. I'm going to talk about something that's really close to my heart, a sport that I'm very passionate about, and that's cycling. I've always been a cyclist. Of course, cycling is a discipline that we've become very good at in the UK. Arguably one of the leading nations now for cycling. And this is quite a turnaround because for many years we weren't the laughing stock of cycling, but we were never really all that good. And we've got amazing athletes now certainly on the track, in the velodrome, leading nation in the velodrome, but now in the Tour de France. And then, of course, athletes like Mark Cavendish as well, incredible sprinter, who's going to hopefully win loads of stage races in the Tour de France, and then come back and hopefully get that Olympic gold as well, one of the first events in the Olympics. It's not just track cycling, though, and road cycling. We're also really good at mountain biking. We've got some of the world's top downhill mountain bikers. We've got the world's top BMXer as well. So really, we're great at cycling now, which is fantastic. But anyway, we're going to talk about cycling and some of the physics behind cycling. One particular bit of physics. We're going to have a look at aerodynamics. So aerodynamics is a subject that you probably haven't really come across that much at school. It's something that we do a lot of, though. Aerodynamics is really important. It really describes the effect that air has on the things that are moving through it. So aerodynamics is really important, obviously, for a bike and a cyclist, but it's really important for a footballer, or it's really important for a tennis player, because when something moves through the air resistance can be really important. And I'll explain why. What goes on in sort of relatively simple terms. Say if you're a cyclist, you're moving through the air, what's happening is you're actually compressing the air in front of you. And so you get this build-up of like high-pressure air, sort of air that's squashed together on the front of you. And then that moves around you. But when it moves around you, you've sort of moved on, and you actually leave a gap in the air behind you. And that gap in the air, you've almost got like a hole in the air, and so you get very low pressure behind you and quite high pressure in front of you. And that pressure difference between the high pressure on the front and the low pressure on the back, that's what creates aerodynamic drag. And it can be very large, this force. If you imagine what's going on for a cyclist, they're cycling, they're putting down power, putting down maybe, say, 200-300 watts of power. It's a big old force that gets turned into. And that will accelerate the bike forwards. Now, if there wasn't a large aerodynamic force pushing you back, that cyclist could just get faster and faster and faster and faster and faster. And before soon, you'd be doing millions of miles per hour. Well, of course, that doesn't happen. And it doesn't happen because there's a very strong force which pushes back in the opposite direction and often kind of matches the force that you're pushing back with. So you end up going at a constant speed. You end up effectively in equilibrium, and you're not accelerating. So the force that this is, we can actually figure out how big that aerodynamic force is. This is our sort of equation that describes really about how aerodynamics works on a bike. That F is the drag force. That is this aerodynamic force that is so important in terms of describing how things move through the air. Obviously, we can figure out what half is. We know what half is. The rho here, this letter here, rho, that's the air density. The density of air in Sheffield is pretty similar to the density of air here in London. There isn't a great deal of difference because we're at a similar altitude. But the air density in, say, Mexico City or on the plains of Tibet is much lower, and that's because you're at a high altitude. There's simply less air around, so you get lower density air. So air density does change, but it predominantly changes with altitude, or sometimes with temperature as well, actually. On a hot day, the air is less dense than on a cold day, which is why in the velodrome at the Olympics, they want a very hot velodrome, because the air is less dense, which means they can go faster. We've got the next term on our equation is v. That's the velocity again. Again, it's a squared term, so it becomes very important in this equation. The next thing is the CD. That's the drag coefficient. Effectively, it describes the shape of the object that we've got. And the final term, A, that's the frontal area. That essentially means if I'm cycling towards you, if you take a picture of me, it's the area of my body that you can see. We want to have a think about what happens when cyclists say they go round a track, they go round the velodrome, and what we tend to see, we see this behaviour where the cyclists follow each other very, very tightly. One cyclist cycles along, the other cyclist is just behind them. Maybe there's a chain of them, all riding very, very close together. And then at a certain point, the lead cyclist will peel away, and the next cyclist will go on in a chain. We call it drafting, and it's something that happens a lot on the track, and it also happens a lot in road cycling as well, where you'll get the peloton will be going round, and the peloton will go to like a spearhead. There'll be a few riders at the front, and then all the other riders are riding very, very close behind them. And there's a very good reason why they do it, and it's because they can actually reduce the aerodynamic forces that are acting on them by cycling very close. Some people have really taken this to extremes, this idea that you can, drafting behind someone, you can reduce the drag forces that are acting on you. For instance, here, cycling behind a train that's moving along as fast as it can go. And you can see here they've actually laid down wooden slats sort of in between the train tracks so the cyclist can cycle along. I think that cyclist is going about 60 miles per hour behind that train on the flat. And he can do that because he doesn't have any aerodynamic forces holding him back, or very few aerodynamic forces holding him back. Now, some people really push this to the extreme, and we've got an example here of someone who's cycling behind a drag car on sort of, I think those sort of salt flats, and this cyclist here got up to about 160 miles per hour on the flat under his own energy. You can see he's got two huge cogs here on the bike, so he can actually pedal at that speed. Actually, the cog is so big, the gear is so big, he has to get towed up to a certain speed, then lets go, then starts pedaling, then accelerates up to, say, 160 miles an hour. Quite incredible, pretty silly, really, if you ask me. But nonetheless, this is what you can do if you remove those aerodynamic forces. So drafting is really, really key. In road racing, it's really important because cyclists will tuck in behind each other and then they'll explode to overtake just at the right moment. So, for instance, here, Nicole Cook, one of the great sort of female cyclists of our time, she'll be doing this. She'll be tucking in behind other riders, using tactics to make them do the work. Then just at the right moment, she'll accelerate past them because she doesn't experience the same amount of drag. Happens in nature as well. Moving through the air, quite a lot of animals will do the same thing. So birds will fly in formation, and they will tuck in behind each other so that they don't experience these high aerodynamic forces, and they'll actually rotate so that one bird will fly and do the work. When they get tired, they'll sort of move to the back, and another bird will take place. And so as a unit, they can move easier. And I've put another picture in there. That's in swimming, it happens as well. So say in events like the triathlon, open water swimming. Water and air, they're both fluids. Same physics applies to both of them. And in swimming, so I do quite a bit of triathlon, so I swim quite a lot. When you're swimming, it's easier to swim very close behind someone else, literally, and you sort of aim, in triathlon, you aim to sort of tickle someone else's toes, get right in behind them, and again, you're moving through a medium which is easier to move through, so you don't experience the same amount of drag. So we see it in all sorts of places. So how does it work? Well, essentially, we have to go back to this equation, okay? So our drag force equation. What we've got going on is that the first cyclist is going to experience quite a large drag force. The cyclist behind will have a slightly lower drag force, and behind them, even lower still. And it's because two terms in this equation are changing. It's the air density and the velocity. And I mentioned this before. If you remember what I said, what happens is the cyclist moves through the air. As they move through the air, they create almost like a hole in the air behind them. And that air there is less dense than it is here. So if you're the second cyclist, the air density that you're moving through is lower than the air density here, which means that your drag force is going to be lower. If that number is lower, that number is going to be lower. So it's easier for the cyclist to move. They're moving through less dense air. That's the first really important thing. What's probably even more important, though, is that what happens is when this air moves around the cyclist, so it moves around, it actually slows down, and it starts to sort of recirculate here. So the relative velocity of that air becomes much lower. And again, that really drops this drag force again. So you can see how this sort of equation links into drafting. So the two things are changing. The air density is changing, and the relative velocity of the air is changing as well. And this really explains why birds draft behind each other, why cyclists do it. And of course, even other examples, things like, if you ever watch, say, a Formula One race where you've got cars sort of going along behind each other, and they draft each other, and at the last minute they'll pull out to overtake. This is what's going on there. They're messing around with that air density and relative velocity. There's another kind of key element to this equation as well, something else that we should have a think about, and that's about area. So the frontal area that you project to the oncoming air is really important as well. And, in times gone by when athletes were riding sort of these slightly antiquated bikes like penny farthings, they would have had a very, very large frontal area. And that's because they're effectively just standing upright, standing tall. And that means that you've got quite a large frontal area. But if you change your position on the bike, you can reduce your frontal area quite dramatically. This is an athlete called Graham O'Bree. And Graham O'Bree was an amazing cyclist from Scotland. And he did some really pioneering work in bicycle aerodynamics. He was a bit of a sort of a bit of a maverick, really. And he kind of designed his own bikes. This bike here had a bit of an old washing machine in it, I think, quite famously. And he could get his body in these amazing positions. So he would tuck his body down onto the handlebars to really, really reduce his frontal area, because that A term in the equation is really quite important as well. So he could get his body in these amazing positions, reduce his frontal area. He actually, in this sort of tuck position, he got a series of world records. Unfortunately, what happened was the governing body of cycling then banned this position because I think they deemed it to be unsafe. So he came back with a different position. He called it the Superman. Quite amazing, really. Just right, okay, you've banned that. I'll come back with another one. So he stretched his body out really far. But again, the frontal area of the cyclist is quite low because of the position he was putting his body into. This frontal area term's really, really key. Now, we're going to try and demonstrate this to you. So I need a willing volunteer. Okay, now, you at the back there, you were really quick, so come on down. That's great. A little round of applause, please. I'm going to hand over to Sean for a moment, who's going to explain what's happening here.
So, first of all, what's your name?
Charlie.
All right. Just to sort of set the scene, how many people have got an Xbox Connect out there in the audience? Right. And out of those people, has anybody tried plugging it into a computer at all? Nobody? That's interesting. Right. Well, as sports engineers, this is a bit of kit out there that we like the look of, we think looks good. We'll have a look at it, we'll chop it apart, we'll do bits with it and adapt it for our purposes. And the Xbox Connect's an absolute prime example of that one. So if we take a look here, we've got a standard off-the-shelf Xbox Connect. Nothing fancy, nothing clever, and just plugged into a laptop with a bit of special software. So this bit of software on the screen you can see here. If you just go and stand in front of the Connect for us, just stand sort of about here. Give us a wave. So you'll see that the Connect's tracked our volunteer. You can see the blue dots that are on the screen. They all relate to the joints of our volunteer. So we've got shoulder joints, elbow joints, and you can see it's showing the height at about 1.73 meters. So that's using the Connect in sort of its conventional sense. So going back to our original application, we can use the Kinect as a 3D scanner, so to analyse the way that somebody looks when they're in sports. So if we switch to our next bit of software, so we can see we've got a normal sort of camera picture on the left-hand side, then on the right-hand side we've got this sort of 3D image that the Kinect will generate. So we're going to get our volunteer now to sit on the bike. So you want to sit on the bike for us? And what we're going to get our volunteer to do is to sit in two positions. So the sort of upright position that you'd normally see when you're cycling on the road. And then later on we're going to use the drop position, this sort of hybrid position that we saw that Chris Hoy uses, where you're on the dropped handlebars. So if you stay in that position for us now. So we're going to use a Kinect, and we have to say to the computer where our volunteer's shoulders are and where the bottoms of the legs are. So we're seeing that the Kinect's calculated the frontal area in that position of about 0.24 metres squared. So if you go on the sort of hybrid drop position, so you go on the dropped handlebars, bend right down as far down as you can go, and do exactly the same. So we can see that's gone down to about 0.19 metres, so about 0.05 metre drop. So relax now. So it doesn't sound like a great deal, but you consider in the Tour de France on a real long distance rate, that sort of change in frontal area can make a massive, massive difference. So thank you very much for our volunteer.
Okay, so frontal area, yeah, absolutely key to cycling. And getting your body in the right position is really important. The next and sort of final part of this story is actually about the shape that the object is. Shape's really, really key. So different parts of the bike can actually be redesigned to reduce the drag that happens. And this is something that we've been doing with British Cycling for a number of years, working on the design of the bike that the British team ride for the Olympic Games. And essentially what we do is we use quite complicated modelling techniques to understand how air moves over different objects. And what we find is it's not just the frontal area that's important, it's the shape of the object as well. So designing shapes like this, these teardrop shapes, can actually reduce that drag as well. So shape's important. And what we do, because we go through this sort of modelling technique, we can actually try out all sorts of different shapes and then find out the optimum solution. So we can go through this sort of this simulation kind of idea, find the optimum shape, and that goes to get used and gets made. And you can make, you know, quite small differences, but if you make enough of these small changes in terms of the design, different aspects of the bike, even looking at things like, for instance, you know, the wheel nuts on a bike, that can, you know, have quite, well, each difference, each change might be quite small, but you add them all up, and you can end up with a, you know, a significant difference in terms of performance. And it's not just the bikes themselves, it's things like I said, things like the helmets as well, and you know, body position on the bike, all these different things come together. So just for thinking about bike design, thinking about this really important drag equation, we can understand drafting. Okay, so tucking in behind each other. What we're doing is we're reducing the relative velocity, and you know, we're reducing the density, and that can make the cyclist that's drafting feel a lot more comfortable. And when it comes to sort of optimizing the design of the bike and the interaction of the athlete on the bike, you know, it's about reducing that frontal area and thinking about the shape of these different components as well. And all those elements get put into that one elegant equation. So if you can master that equation, you can master bike design. Okay, so we're going to move on to our final topic. We're going to talk about running. Of course, this is one of our great Olympic hopes, Mo Farah, a fantastic sort of middle distance runner. I'm going to ask you a question, actually. So we've got some microphones at the ready. Okay, so it's a pretty simple question, but I want to see if we can get some good answers to this. Why wear running shoes? I'm sure most of us have probably got a pair of running trainers somewhere, or just a pair of normal trainers. So why do we wear running shoes? Let's get some answers. Come on, don't be shy.
They manipulate the air.
To manipulate the air, yeah. So aerodynamics. I'm not entirely sure about that. There have been some designs of shoes that have definitely brought that into it. So some running spikes will have covers for the laces, and they'll be as sleek as possible. If you're a cyclist, having a sock over your shoe is really, really key. But have we got some other sort of ideas? So we've got one here.
They add traction so you don't slip.
Okay, traction. We'll come back to that. That's brilliant. Okay, another 2 here.
I don't think it's really related to physics, but I know it because it's like more soft. It reduces like I can't describe it, like the force, and it stops shin splints.
That is absolutely what physics is, though. That's forces, that's motion, that is physics. It couldn't be more physics. Great. And another one here.
Isn't it more comfortable?
More comfortable, okay. About force, about cushioning. So we had sort of traction, reducing forces. Well, there's a lot of different reasons why we wear running shoes. I think we wear them for cushioning, just like we said here. I'd say it is physics, absolutely is physics. So yeah, cushioning, shock absorption. We also mentioned traction, grip. So essentially, when you're an athlete, you're putting force down through the ground, trying to propel you along. Well, if you've got any slippage, you're not going to sort of make the best use of that force. So traction can be very important as well. I think something we maybe didn't mention is protection. A lot of us live in an urban environment, and it could be glass and stones and all sorts of nasty things on the floor that maybe we don't want to be running, say, bare feet on. So we want some protection there as well. There are a couple of other ideas. Some shoes get sold with this idea that they can maybe correct the way that your foot hits the ground and create stability in your footfall, maybe try to modify aspects of what we call your gait, how you move. So that can be an important thing. I think one of the biggest reasons myself is probably fashion, how this thing looks. We want to have something that looks pretty nice on our feet. I think that's a very, very strong driver for it as well. Who thinks that running shoes can make us run faster? Let's have a show of hands here. Show of hands, who thinks that a running shoe makes you run faster? Okay, we've got, what do we reckon? I think it's probably about 2/3. Who thinks that running shoes don't make you run faster? Okay, we've got a few hands here. Okay, all right. So that's interesting. I'll try and delve into that a little bit now. Why not just run barefoot? Okay, this might sound like a radical idea, but actually this is something that people think very seriously about. Something that I think a lot about, actually, and there's some good reasons behind this, so just try and follow me here slightly. Humans have only been wearing shoes for maybe, I don't know, say 3,000 years, 5,000 years, something like that. We've only been wearing running shoes since the 1970s. So in terms of our sort of evolutionary history, running shoes have come in the tiniest amount of time. And then now we seem to be incredibly dependent on them, think we can't possibly run without them, which, of course, I consider to be ridiculous. And it's because, as a species, one of the main reasons we're all here having sort of interesting intellectual discussions is because we could out-hunt other animals on the sort of the plains of Africa. Believe it or not, okay, all of us are incredible endurance athletes. We can outrun most animals, and it's not because we're faster, but it's because we can regulate our temperature, we don't overheat, because we can sweat, we can keep our core temperature down, whilst other animals will overheat and will eventually get to exhaustion, and they'll sort of keel over, and then we can eat them. And because of that reason now, then our brains get bigger, and it's part of the reason why we're here. Now, when people were running around after animals and being so successful at it, they weren't running around in a pair of Nikes. And so you think, well, do we really need these running shoes? Do we really need them? And there's some other good examples. So, for instance, Zola Budd here, breaking 2 world records running barefoot. So this idea that maybe we have to have a pair of running shoes to make us run fast maybe isn't necessarily true. Now, I'm going to need another volunteer here to sort of delve into the physics of what happens. I think you had your hand up first, right on that row there. Can you come down for me, please? Well done. Well, I'll pass over to Leon, who'll take us through this.
So what's your name?
Jordan.
Jordan, thanks, Jordan. So should you come over here, Jordan? So in sports, a lot of things happen at very, very high speeds. So as sports engineers, to understand what's going on, we need to slow what actually is what's occurring down, so we can actually examine and analyse what's going on. So in as sports engineers, we use high-speed video cameras. And Jordan, you can come around here. And what we've got here is actually a high-speed video camera set up behind this desk here. And so what I'm going to get Jordan to do is actually run in front of this camera. So Jordan, if you want to come down with me over here. Okay, so this is on the screen now. We've got the feed that's actually coming from the video camera. So this camera operates really, really, really fast. And the shutter is actually going really, really fast. So we have to have the area flooded with as much light as possible so that enough photons can get to the center of that camera. Okay, so Jordan, could you just do what I'm going to do in a second? I'm just going to jog across here. And I'm going to put my foot, land it in here. So if you do the same thing, exactly what I'm doing, well, like that, and just carry on and jog through like this. Okay? So, Sean, are you ready? Okay, Jordan, go for it. That's good. Did we capture anything? There you go. Thank you. Okay, so I think we got something there, Jordan. So, should we give a round of applause for Jordan? Thank you, Jordan, for the shoes.
Can we get that on a loop? That's fantastic. So you can see what Jordan's doing there. If you just have a look at exactly what's going on, his forefoot is hitting the ground first. There's sort of a number of different ways that people run. The part of your foot that hits the ground first is really key in terms of really just determining the whole way that force interacts with your foot. Now, there are two main ways that you can do this. Some people hit the ground with what I call their midfoot, the balls of their feet. And then what happens then? Something really interesting happens. Your Achilles tendon, which is on the back of your ankle here, that acts like an amazing spring. It's an amazing shock absorber. And it's very elastic, and that takes your heel then, because it goes down to the ground. You don't lose much energy, and it sort of springs back into place. And what happens is we get this quite a nice, gentle build-up of force and quite a nice, very well-cushioned impact. The other way of running that a lot of people do is they'll run along and they land with their heel first. So their heel is the first thing that hits the ground. What happens when your heel hits the ground first is your Achilles tendon can't do anything. This sort of natural spring mechanism doesn't work. It's just not there. And it's because there's effectively a very large stiff bone that goes from your heel straight into your knee, which is why if you heel strike, say if you're not wearing a pair of trainers, it's going to hurt a lot. And if most people were to take their trainers off and start running, they'd run with their midfoot and their front foot. So you rely on this sort of natural sprung mechanism that you have inbuilt into your body. And I think what happens, and this is really interesting, when people put on a pair of trainers, because of the shape of the trainer, because you've got this big cushion under your heel, the cushion has to be under your heel because there's no spring otherwise, you have to cushion the heel. That trainer, we think, probably makes you heel strike. We've got some evidence to suggest this, so people have gone to Africa and they've looked at people who have never worn shoes. People have never worn shoes when they run. They run on their midfoot, their front foot, and they rely on this Achilles tendon. Give them a pair of trainers, and what happens is they heel strike. So the trainer is actually making us heel strike. And so we lose this sort of natural inbuilt spring that we have and then have to rely on the technology. And that's kind of led to all sorts of people thinking, well, do we need running shoes? Are running shoes actually good for us? Are they making us move in a way that isn't really very natural? And, this millennial revolution, we've got this wonderful way of running, and the running shoe might actually be spoiling it in some way. Now, there's people on different sides of the argument, which is really healthy, and that's the way that science works. We sort of debate these things and eventually might come to some greater level of understanding. But there's certainly a large body of people now that feel that we shouldn't necessarily be heel striking and actually designing new shoes that provide you with, say, traction, so you can do the grip. You can have a bit of protection, so you're not sort of, running barefoot necessarily on sort of glassy glass on the streets and so forth, but they don't make you heel strike. And that's maybe an interesting way to go forwards. I've got just a couple of minutes left, and I'm going to talk about another type of running, something that's kind of even more radical as an idea, and that's these pair of legs. So obviously these legs belong to an amazing athlete called Oscar Pistorius, who we'll definitely see in the Paralympics in September, and we there's a very small chance we might see him in the Olympics as well. So this is an athlete who can run as fast as the very best 400-metre runners and has actually been given a licence to compete directly against non-disabled runners. But he doesn't run wearing a pair of running spikes, he runs with a pair of running blades, a set of carbon fibre blades that have been designed and optimised to give him a really good running technique. And it's been really quite a controversial topic, actually, because it's a big question around, essentially, you know, are these running blades, are they just enabling him to run, or are they enhancing his running technique? And this is a discussion and an argument that's been sort of rumbling on for a number of years. The way that this sort of topic has been sort of thought about is essentially, it comes down to a question of science. Does he have an advantage or doesn't he? And it's quite a complicated problem. I'll try and whiz through it as best I can. Essentially, running with running blades, you've got some different physics is going on. A few things to talk about that. Essentially, running, sprinting, is a series of jumps. Consider it as a series of jumps, and to jump, you've got to create a large ground reaction force. You've got to generate a large force. Now, experiments have done with Oscar Pistorius. He can't generate these large ground reaction forces, so he seems to be not doing as well as other sprinters. But he can win in other areas. So, for instance, because his legs are so light, they're made out of carbon fibre, they're lighter than muscle and bone, he can relocate his legs faster than other sprinters. He's got a faster stride than any other sprinter ever. So he can relocate his legs really quick, and that's really important. Stride frequency is a key indicator of how fast you can run. It's got another big advantage as well, and that's when you put your foot down when you're running, you generate a large force which pushes you backwards. It slows you down due to that contact with the ground. You get a large braking force. Because of the shape of the running blade, these braking forces have been reduced very considerably, and that means he doesn't have the same amount of braking force. Now, you add that together, and you do experiments on him, and people have done experiments, and they measure how much oxygen he's breathing when he's running at speed, and he uses less oxygen than other non-disabled runners. So when he's running at speed, he seems to have a higher running economy. He uses less energy. It's easier for him when he's running at speed. But we also know that he has a massive disadvantage when he's accelerating off the blocks. So when he's accelerating and getting up to speed, he's much, much slower. And then maybe when he's at speed, that kind of balances out the disadvantage he's got. So it's all quite complicated and lots of different things happening. But it's amazingly intriguing because here we've got an athlete who is supposedly disabled, who is out running, doing incredible things. I'd describe him as being super abled, and technology is very much part of that. And I guess it asks, or it sort of delves into this ground around, well, where is this going? Where is this going as a piece of technology? What will the future possibly look like? Well, it's not really the future. It's kind of here already. So, for instance, this is a guy called Hugh Hare, who's a bilateral amputee, a double amputee. He's also one of the leading scientists looking at sort of the use of prosthetics. He's based in America, and he has claimed, and I think I'm probably right to believe he will do this. He thinks he'll be able to run faster than Usain Bolt because he's got powered prosthetics that literally charge him along. And it's really interesting. It's quite amazing. This stuff used to be the stuff of science fiction, but it's not actually. It's here now, and it will only get more and more and more as the years go by. And that's incredibly exciting. And of course, at the same time, there's some interesting questions there, not least being, what it actually means to be human. And so some very interesting territory there to think about. So I'm going to leave it on that sort of big sort of future kind of thing, and say thanks a huge amount for sort of listening so well. I hope you enjoyed that. I hope you kind of can now see a bit more of how physics and sport links together. If you've got any sort of questions or ideas, things that you want to know more about, we've got an amazing blog that we write. We put new blog posts up there sort of twice a week or something, answering all sorts of questions to do with loads of different sports and all the different physics and engineering that happens in it. So have a look at engineeringsport.co.uk, and you can ask us questions on there and do all sorts of things as well. And finally, just to say, final thing really, all we've done here is talk about a very small part of physics in one specific application and discipline. But physics is everywhere. Physics is just absolutely, wherever you look, there's physics. And it really is interesting. There's so many different varied careers you could go into, different avenues, different opportunities. So we've just shown you a tiny little bit of it. I hope it's been interesting. But I'm just, my take-home message is that if you are interested in this sort of thing, just make sure you do A-level physics, because that really opens up everything for you. So on that message, I'll say bye. Okay. Minimise it, say for the cyclist or the swimmer, but in other cases we're trying to maximise the friction. But we can't go too much, because for instance in this case if you had too much traction on your feet you might end up actually doing yourself an injury. So it's actually about optimising the amount of friction that we've got. So it's quite a difficult problem often. And I guess the final thing that we focus a lot of our efforts on is it's trying to measure the world of sport. Sport's very complicated, lots of things are happening, people are running around all over the place, balls are flying from left to right, and all sorts of different things can be happening. And actually information is one of the key things that can really drive performance. If you can measure what an athlete is doing, you can provide really valuable information, say, to the coach, so that athlete can train better, train harder, train more effectively. So increasingly, what we do is we're actually about measuring everything that's happening in the world of sport, and then trying to decipher all that data, analyse all that data to pull out the really important things that actually mean something. So we're working at the moment with 14 different Olympic teams, all Team GB, glad to hear, and I think about 20 odd different projects with those teams as well. And it's all about trying to measure what our athletes are doing and then filtering that information back to the coaches so they've got a better idea of what they should do. And of course, it's not just about providing information, say, for the coaches. Sometimes it could be about providing information for the referees. So, goal line technology being a key example of how we might want to measure something, so that can actually sort of have an influence maybe on the outcome even some games. There are sort of key areas. What I'm going to do in this talk, I'm going to talk you through a number of different Olympic sports, and we're going to have a look at the underlying physics behind each of those sports. So our first sport to look at is the long jump. I guess we're going to start off with a bit of a scientific hypothesis, and that's who we are and what we do. So I call myself a sports engineer, and we've got a research centre up in Sheffield, and we do lots of different things. Essentially, we try to kind of understand the fundamental physics of what happens in our sports, and then we use that knowledge to try to create new products, create ideas, to work with athletes, to make them be better at what they're trying to do. So sort of things we do. We look at things like forces are very important to us, understanding what the fundamental forces are, where they're acting, how big they are. That's a really good starting point. We also spend a lot of time looking at materials. The world of sport's gone through a sort of a revolution in terms of the materials that get used. So, for instance, tennis rackets have developed from, say, wooden tennis rackets in the sort of late 1970s and early 1980s into carbon fibre tennis rackets today. That's actually quite a recent change, but a very, very dramatic change. So you might see John McEnroe on the television over the next couple of weeks as he commentates on Wimbledon. Well, of course, he used to play tennis with a wooden tennis racket. And so these things are changing. And not just that, obviously, we've got the European Football Championships happening at the moment as well. Well, football in the 1960s was played with leather footballs that used to absorb moisture off the grass and rain, and used to double in mass during the game. And of course today we play with balls that are quite different, thermally bonded synthetic balls that are altogether quite different really, and that has implications for how the game is played. So materials are really important to us. I guess another area of things we look at is we look at friction and traction. So obviously in this case here we've got an athlete who's clearly lost some traction and has probably lost the point as a result of that. So understanding how friction and traction works is really key. But it's not always just about, say, footwear. It could be about how, say, a swimmer is moving through the water, or how a cyclist is moving through the air. The role of friction in sport is really critical. So we try to understand it. And sometimes we're interested in trying to My name's Dr. David James. I'm a lecturer in sports engineering at Sheffield Hallam University. Our lecture for the Institute of Physics Schools Lecture Tour is really a story about the interaction between physics and sport. We delve into 3 different Olympic sports and we unpick the physics that governs those sports. And really it's all about forces in motion, it's all about Newtonian physics, and we deal with this sometimes quite a challenging topic through the context of sport. And I think the students find it really, really exciting and interesting. I think I probably first got really interested in physics at some point in secondary school. I think I remember being taught about, particles and then atoms, and just being amazed that there was this world that we can't see with our own eyes, but that is absolutely fundamental to everything we do. And this idea that there's this incredible unseen world that explains everything, for me that was just such a fascinating idea, that there was this incredible unseen world out there. I found that it's really turned me on, and I just really had to know more. Welcome to the marvellous Royal Institution. My name's Dr. David James, and I'm here today with 2 of my colleagues from the Centre for Sports Engineering Research at Sheffield Hallam University. So we've also got Leon Foster and Sean Clarkson, who'll be helping us out over the next hour. Obviously, we've got the London 2012 Olympics just a few weeks away now. It's been a huge build-up. I'm sure it's going to be a fantastic games. But throughout that event, I'm sure you'll probably start to see this as I go through this. Well, I hope that when you see that event, you'll see that there's so much science going on sort of behind the scenes all the time. So, first of all, just a bit about distance jumped was just about sort of 4.9 metres or something like that. So that's the data set we've got. And you can see there's been big changes. Okay, so obviously in the 100-metre sprint, times have come down really rapidly. They've kind of levelled off. Equally, in the long jump, distances have gone up and then levelled off. What I find amazing is they seem to be quite symmetrical in terms of the shape and the profile. And they've got very similar features. So for instance, here and here, you see there's sort of this dip in performance. And that coincides with the Second World War, which I think is really fascinating. So during the Second World War, obviously, it's has such a global impact on our world that people just couldn't participate in sport. They had far too many other things to be worried about, so sporting performance dropped. We see another interesting trend here, is that really both in the 100 metres and especially in the long jump, after sort of 1989, 1990, performances level off, or they go down until that date, and then it goes level. What's quite interesting here is 1989 was the year that widespread drugs testing was introduced, and that's when we see a very significant change in how our athletes are performing. Now, I'm going to just manipulate this data slightly, and what we've done here is I've actually represented the 100 metres, not in time, not the performances in time, but in actual speed. So average speed, and that means that we can just compare these 2 data sets a bit easier. So you see they're very similar. We can actually correlate these 2 data sets now, plot them against each other, and we get this really nice correlation. Very strong correlation indeed. So they all line up on a line, and so we've got the female data there in the red dots, and then the blue dots are the males, and it's all on a nice sort of flat straight line sort of continuum there. So we've got a very strong relationship. That's a high, is that top sprinters equal great long jumpers. As a question, do these 2 disciplines go together very nicely? There's quite a lot of anecdotal evidence to suggest that this might be the case. For instance, Jesse Owens in 1936 is one of the all-time great athletes. He won the 100-metre sprint and he won the long jump. However, that's just one example, so I don't know, maybe it's true, maybe it's not. We've got some other examples as well. We've got other fantastic athletes. Carl Lewis, again, an amazing sprinter, won gold medals in the 100 metres and also won gold medals at the long jump. So you've got the athletes seem to be able to move between these disciplines quite easily. And also, of course, Marion Jones, slightly more recently, winner of the 100-metre sprint and at the long jump as well. But we can't just use, these anecdotal bits of evidence. We have to sort of really delve deeper into the data before we can start to maybe draw any conclusions. So what we've got here is we've got a massive data set, and I'll try and talk you through it. Essentially, what we've got here, so first of all, these are years, these are dates on the bottom, so we're going from 1918 up to 2010, 2014. And each data point represents the average of the top 25 performances in that year. So it's a huge data set, this. So we've gone through all the record books and figured out who are the top 25 competitors in any year. This is a global data set. Who are the top 25? And we've figured out their average. We've plotted it on a graph. And we've got two data sets here. So it's a tiny bit complicated. We've got the 100-metre sprint in time here. So in 1922, if we go up here, we can see that the average 100-metre time for female sprinters was just more than 13 seconds. We've got another data set as well. We've got the long jump. Okay, so on the long jump in the same year, 1922, the average